So we're going to introduce that today. I'm going to introduce that today and tell you a little bit about what we're going to be doing. Really, this is kind of a way to take some of the material we're learning in Chapter 8, apply it to a more real-life-ish problem. And what that's going to be is the design of a pumped hydro facility. So if you've never heard of pumped hydro, you will have heard of it after this. This is an aerial photograph of the pumped hydro facility up in Ludington. Has anybody ever been there? I see a head nodding. Hans, you've been there? Yep. Large, impressive. Did you go inside? Or no, did you just saw from it. Okay, just saw from a distance. So if you can actually drive, it's hard to see. I don't know, but right like around there, that's a road, so you can drive like right between the reservoir, which is that little lake, and Lake Michigan. So it's situated, a reservoir is up kind of on this bluff right along the shore of Lake Michigan. You can drive up there, it's right fairly close to the town of Ludington. So why do we care about pumped hydro? One, because it's kind of a cool fluids problem. It also has some relevance to energy today because it's an energy storage facility. Essentially, it's taking hydropower, and instead of putting hydropower on a river, you're putting it between two separate bodies of water. So this picture here on the left is the largest battery storage facility presently in the world. It's in Australia. It's coupled to a fairly major wind and solar installation. It's something, I'm going to get my numbers wrong, but it's something like 100 megawatt hours at 100 megawatts. So it's similar production, not quite as big, but similar production to the Holland power plant. But it can only run for like an hour before it's out of juice, like if it's running at full power. So fairly large, but that's about the biggest storage that we have currently anywhere in the world in batteries. The largest storage facilities presently, and about 95% of what's currently on the grid worldwide, is pumped hydro. So pumped hydro has been around. The Ludington facility was built in the 70s. And it was built coupled with a nuclear power plant, basically so that the nuclear power plant could run at full capacity all day, every day, all the time. And when electricity is in greater supply than the demand, basically what you do is you pump water up the hill. When you need electricity, you let the water come back down the hill and you use that to generate electricity. So what you're going to do is do some of the analysis, the fluids analysis of pumping efficiency and where are the losses and how do we, when we're generating electricity, what does that look like for this facility? Okay, so I was a slide ahead of myself. So there are 184 gigawatts of installed capacity worldwide for pumped hydro. That's a fairly large amount. Some of the brand new, like proposed to be completed in the next couple of years, battery installations are getting close to about 1 gigawatt. So it's going to be, batteries are obviously a major part of grid storage, but pumped hydro is like the present major component of grid storage. But it's not, obviously, we don't have a lot of storage on the grid. It's still a fairly small component compared to total energy demand. But basically what you do is you design it to be able to deliver maximum power for some number of hours. So you couple it with some either like renewables, or you couple it with something like nuclear power that you want to run at 100% all the time. A nuclear power plant, you don't run like a coal or a gas power plant. You can kind of ramp up and ramp down as demand goes up and down. Nuclear power, you want to be like running at 100% capacity all the time. When you're turning nuclear reactors on and off, that's a whole big process. It's very slow. You want it to just be 100% all the time. So you couple it so that you're producing power at some part of the day when you need it, and you're using the excess power to pump water when you have excess power. So you can imagine coupling this to renewables, and when it's super windy at night and there's relatively low energy demand, you're pumping water up the hill, and then when it's a calm day, and there's extra energy demand, then you let the water flow back down, and you can use that to kind of buffer energy demand. And that's how you as a utility make money from these things. When they sell it to you at 10 cents a kilowatt hour, 12 cents a kilowatt hour, but when the energy costs them 1 cent per kilowatt hour, they pump it up the hill, and then a little bit later, they sell it back to you for 12 cents. So the problem that you're going to have is going to be intentionally somewhat similar to the Ludington pumped hydro facility. That's to give you some kind of basic guardrails, I guess I would say. You're going to be working on this project in groups of 2. So the first step for this is just to choose your group. So that will be the first part of the project. Basically, the goal is to size the major equipment. Like, how big of pipes are you going to need? How many pipes are you going to need? How big of turbines are you going to use for this turbine/pumps? How big are these things going to be? Calculate the key performance metrics. What would be the efficiency? So if you wanted to store 100 megawatts of electricity that you have kind of sitting around, you want to store it in your pumped hydro system, right? You use that electricity to pump water up the hill, and then you get that electricity back when the water flows back down. But there are going to be losses in that from your turbine, from your electrical generator, from friction in the water. There are going to be losses from all of those places. So your job for fluids, we're not going to really focus on the design of the turbine or generator in a whole lot of detail, other than to see kind of how they fit in the whole picture. Your job is to kind of solve the fluids problem. So how do we set up a system where we can look at losses as water is pumped up and down? How do we size the pipes? How do we figure out where these losses are in this particular system? So that's going to be your job. And essentially what you're going to do is build a model, and then use your model to ask specific questions, kind of to do what I would call it, to do specific experiments on your problem. So you're going to build this mathematical model. It's going to feel like kind of a complicated homework problem. But I think the interesting part of the problem is then, how do you take this model and use it to ask questions? Like, what happens if we increase the pipe diameter? What happens if instead of, this set of assumptions that we used, if this is actually true, or this is, if this part changes a little bit, how does that affect it? Does this matter at all, or is it basically doesn't matter? So we wouldn't have to invest a whole lot of time in optimizing or kind of engineering that part of it. But this other part, maybe there are seasonal effects. Maybe there are redundancy effects, like if you have just the whole system set up on one turbine and that has to go down for maintenance. So you're going to be thinking of stuff not just in the fluids context, but trying to think of it in as broad of a context as you can. Understanding losses, the relative importance of different factors, so you could suggest kind of, what are the key parts that are really the biggest contributors to losses into the design or optimization of your system. So there's not going to be a single solution, obviously, but you're going to be looking at how do we kind of take all of these different things into account. This is just a small snippet of what kind of the outline that I have for this. There are going to be 2 different reporting kind of mechanisms for this. So there's going to be an introductory report, which is basically for you guys to look at some of the initial project documentation, think a little bit about how you might want to solve it, write up kind of a brief, this is kind of our outline, these are some of the equations that we might use, this is how we're thinking about putting this together. And really, it's an opportunity for me to give you some more, for you to have looked over stuff, thought about it, for me to give you feedback on your initial path or trajectory. So you'll have some initial sketches, maybe example calculations, maybe some outlines of a model, not have anything solved, but just to get some extra direction. That's going to be due Friday, April 9, so a week from this Friday. And like I said, really that one, it's going to be worth about 10% or 20, I can't remember. I'll have to look a second. 10 or 20% of your final project grade. It's not going to be graded very harshly. It's more for like, I want to see your initial ideas to be able to critique them and give you direction where appropriate. The final design report is going to be maybe a 2 or 3 page-ish, single spaced. So it doesn't need to be super long, but it should be a report detailing your design decisions, design process, the insights that you've gained based on your analysis. So what specific insight do you have that you can recommend for this project? What my kind of initial, just as you're thinking about this, the basic thought or outline that I'm thinking is, you're somebody working for, okay, I guess let me back up. So typically when new power projects are built or designed, a utility like, say, the Holland BPW or like Consumers Energy, they'll come and say, we need, we've done some forecasting for load for our specific utility. We need this much power, and we need it by 2023. Like, to be able to meet load in our area, this is what we want. We want 50 megawatts of new power. So then they'll come to specific contractors and say, what would that look like from you guys? And the contractors will come up with a bid and say, well, we're going to be doing that 50 megawatts, and we're going to be doing this type of a wind installation, and we're going to couple it with this type of storage, and this is what the cost is going to be, and this is how the performance is going to look, and this is what the system would look like. So I'm kind of envisioning you should envision yourself as in part of that like contractor initial bid phase. Like, you're trying to kind of put the outlines on what a storage facility like this would look like, so that your company could get detailed cost analysis and what would be the construction cost, what would be the operation cost. You're acting as kind of one piece in that initial bid type puzzle, if that makes sense. So your job is to communicate via a technical report to your superiors, other people in your company. These are the kind of the broad strokes optimization of a system like this. Again, it's not in a whole lot of detail, not like in the type of detail that you would need to actually build the system, but in the type of initial detail, sketch, technical detail that you would need to be able to price out for something like an initial bid. So that's kind of where I guess I'm picturing you guys, which again is a situation maybe some of you will find yourselves in your career. Like, how do you do an initial analysis to be able to bid out a project for some client? So the technical report should be communicating the key insights of your design, where your analysis says, one of the things where your analysis says, like, this is the really important part. This is where, if we change this parameter, things change a whole lot. That's a really important parameter. Maybe we need to do some more investment and really nail down what that parameter would be. This other parameter, well, we change it and nothing really happens. So we can save that to like the very end, where we're actually like going into the detailed design of the system. We don't need to know that exactly at this point in the process to be able to bid out the system, because it doesn't really matter that much anyway. So those are some of the things that you can be thinking about. That's going to be the technical report. It will be due Monday, April 26th. So there's a fair bit of time for that. And that's going to be, there's going to be a report document. It said 2 to 3 pages. And then coupled with that will be your model. And I'll kind of be looking at both of those things, both your model or your solution and your technical report. So the system as a whole, just to give you a little bit more info, there's now this is on our course Moodle, there's now a design project section. So I'll put all of the design project stuff because it's going to last over a couple weeks. That will just live in this design project section. So I gave you kind of a brief introduction. There's this design problem document. So your first step is, really going to be go over and read through this. So this has the exact specifications. Your company has already cited a specific location on the shores of Lake Michigan, so you know the rough outlines of where that location would be and what would be the height difference between your reservoir and the lake, because that's essentially how you're storing energy. It has some of those kind of initial things. It also has a lot more detail on what I expect for the introductory report and what I'm looking for in the technical report, along with like, this is how many points this would be worth, and this is how many points this other thing would be worth. So it has a lot of info in there. I think it's 5 pages. So there's a lot there. Some of it you don't have to care about yet. Like there's a whole bunch for the final technical report. You don't have to care about that yet. But it's good just to, at this point, go through. This will be kind of your home where you'll come back to what are we supposed to do? What are the, what is worth how many points? This should be a good spot to come back to. Let me see. There's also so I also have the slides I just showed are up there. The first step for this is going to be selecting teams if you want to. If you don't particularly care, come Wednesday, I'll just assign teams for the remaining people. But if you do care who you want to work with, there's a link to a spreadsheet. Looks like some people have already hopped on, which is great. I don't mind if you sign up cross-section. So if people in this section sign up with the people in the other section, that's fine with me. Just so I want you to just write your name and which course section you happen to be in. But it doesn't matter if somebody's in this section or the other section of fluids. If you haven't signed up by like Wednesday after class, then Wednesday afternoon I'm going to go and kind of randomly assign people to teams. So if you're not on this, by that time, you'll get thrown into a team, and that will work out fine. Yeah, so I think, like I said, there's a lot of stuff there, especially in that problem document. So I'm not going to go over everything in kind of exhaustive detail at this point, and we'll kind of go over it in pieces as we go. But are there any general questions at the outset? Yeah, Liz.
Monday, is that going to change?
So that's good thought. So the syllabus, we're about 2 class periods behind at this point, which is actually pretty good. But the intro report, if you looked at the syllabus, that was due, I think, on Wednesday, like in 2 days. So it's obviously not, so I shifted some of the dates for, thank you for that, because that's the other, so there's a new version of the syllabus up. So this intro report will be due on the 9th. Then the final report, that's wrong. I'll update this again because that's not right. The final report's going to be due on the 26th. So that gets bumped back a week. So everything kind of got bumped back a week. The final report got bumped to the 26th, and the exam got bumped back a week to May 3rd, which is not my favorite because that's getting close to exams, final exams. But I guess I can maybe open it up. I would be fine moving that to the 30th, but I think it's probably better on the 3rd. That was my take thinking about it. So I think unless there's some uproar as we get closer to that date, then we can kind of cross that bridge when we get to there. But tentatively, I'm assuming that exam 3 will be on May 3rd. Yeah, so I'll have these updated dates updated yet again because apparently I uploaded the wrong thing. Okay, are there any other general comments, questions at this point? Yeah, I'm assuming there's kind of more information than you have time to process right now, which is fine. And we'll kind of take it as bite-sized chunks as we go along. Okay, so if you care about your team, find a partner, sign up on that spreadsheet. That's step 1. Okay. There is just a couple other comments. So there is a new homework posted, homework number 8, which is also due not this Friday because we don't have class, but a week from this Friday. So it's a little ways out. I guess my comment on that, some aspects of that homework may take some thought. So depending on how well versed you are in differential equations and how happy that makes you. It is going to be the most math heavy, at least I think the most math heavy assignment that we'll have in this class. So just take a look at it. The one comment that I'll make regarding that, and this is a very important comment, use your book, especially for problem 1. Problem 1, if you don't use your book, you could do it, but if you use your book, you'll be much happier. So I would say, especially for that, use your book for that assignment. I don't think none of the math is beyond you guys. So I'm not trying to assign you anything that's super crazy, but it is more math heavy than more differential equation stuff than our typical assignment. Because it's looking at the solutions to the Navier-Stokes equations. So that's homework 8. It's going to be kind of redoing what we did last class with flow between 2 parallel plates, but problem 1 is going to be looking at flow in a pipe. So it's very similar, hopefully with the notes and the book, I think you'll be just fine. But that's not due for a little while, but I guess I would encourage you, we have kind of a lull in this class because we don't have anything due on this Friday, but we have like 2 things due the next Friday. So just make sure you keep plugging away at that. The other plug that I will make, we're going to be jumping into stuff that is related, especially conceptually. A lot of the stuff that we're going to be doing with pipe flow is related pretty closely to Bernoulli's equation. So we spent some time in chapter 6 talking about that. This video that I have here, I think does a really nice job. It's only like 15 minutes or something. I didn't make it. It's people better at videos than me, which hopefully will make you happy. But people better at videos than me made this, I think it's a nice summary. It hits on a lot of the key points. It's fairly visual. So I think that's just a good thing. When you have 15 minutes sometime, just pop that up and rewatch it. And I think it will give you, hopefully, some better intuition on how Bernoulli's equation works, which I think will be helpful as we go on in some of the stuff that we're going to be doing over the next couple of class periods, really over the next 2-ish weeks. So I threw that up there because I think that might be useful. All right. So where are we? We ended last class looking at this. The screen just turned off. That. Okay. There we go. We ended last class looking at this. Right, this draining tank And we ask the question, why is it behaving the way that it is? And we're going to unpack that a little bit this class. So remember, just to remind you what happens, initially we start out at some slow velocity. The tank drains, our pressure difference changes, and all of a sudden we switch from a slow velocity to a faster velocity. So the only way that that can happen is we switch from some state where we have kind of a lot of friction to some other state where we have less friction. Remember, this happens, you can see it's still pulsing a little bit, and then it's fairly stable. A couple other things to just look at. When it's in this like slow state, look at especially right at the bottom of the fluid, you see how it's shaking around a little bit? Right, it's not a lot, but it's kind of flickering and shaking and moving, so the velocity is not super stable. It's changing a little bit. When we go, especially right at the very end, right, this is the faster state. Look at how much more stable that velocity is. Right, it's not really moving at all. So what's happening here, we're switching between two distinct states. You may have heard of these before. One is kind of where we can see through the water really well. We can see the black lines behind it. We call this state laminar. And we have another state where we can't really see through the water at all. We would call that turbulent flow. Just to look, again, a little bit at what that looks like in real life. This is going to be an experiment where we're injecting dye into a pipe and slowly increasing the velocity. So we're increasing the flow rate, we're increasing the velocity, and we'll see a little bit what happens to that dye. So this is laminar flow. We see this nice line of dye. We would say, okay, that's going to be the path line. Oh, and then we start to see some wiggles in it. So we're starting to increase the flow rate, We're starting to get some wiggles in the velocity. We increase it a little bit more. And then we're going to increase it a little bit more. And we get kind of more and more wiggles or fluctuations. And then eventually it just turns to that. Right? Where stuff is going from these nice smooth path line to stuff mixing all up everywhere. One more thing to look at. This is the St. Joseph River. So this is in South Bend, Indiana. It's like right by where I used to live, where I went to grad school. I didn't take the video, but this is a dam right on the St. Joe River. And you can see the top half of the dam, the water is nice and smooth as the river goes over it. And then you hit this really sharp line where you go from a smooth flow to all of a sudden, the water gets really ripply. I don't know what just happened. Okay, I guess we won't watch it again. There we go. Yeah, so you get like all the way down that middle, you get this really sharp transition between where the water is flowing smoothly over the surface to all of a sudden where you start to see ripples and a lot of mixing going on. So that's kind of the defining feature of laminar versus turbulent flow. Laminar flow, it's going to be where things are smooth. Turbulent flow is where we have lots of mixing going on. So let's take, I'm going to put away the videos for a second and let's get out our notes to be able to talk about this and try to develop some of the language that we use. Okay, so Okay. I don't know why this is so small. So laminar versus turbulent flow. This is a really important concept in fluids generally. So when we have laminar flow, when we talk about laminar flow, this is flow in nice layers. This is where it gets its name. Lamina, from the same thing as laminate, the same root, where you have kind of, these nice layers of fluid. So this is, there's basically no mixing. Between layers. And we have, right, I guess let me draw a picture. So this is, you would have something like this. Say there's this pipe. We could draw the velocity like this. We could calculate analytical solutions. Analytical solutions are possible. So even if you have laminar flow, you can't always get analytical solutions and crazy geometries and stuff, but they're at least possible. But even when you can't get an analytical solution, computational fluid dynamics, CFD, you can get a really easy solution numerically. Okay, it's straightforward. Easy to do. You can do it on your laptop. It doesn't take a supercomputer. It's easy. You hit go, pop, it spits out a solution, and it's accurate. So we can know velocity. Really at any point that we want. We can know the right, so we could find the flow rate. We could find shear stress. We could find pressure drop. We can find the pressure difference or pressures kind of anywhere that we want. So basically, for laminar flow, we can come up with the type of mathematical models that we talked about last time, where we can calculate flow rate, we can find max velocity, we could find kinetic energy, we could find any of these things, we could find momentum, we could use Reynolds transport theorem, like all of these things that we've done, we can do all of these, and we can do all of these essentially exactly. So if you want to know, if you have laminar flow and you want to know what the forces are on a system, if you want to know what the flow rate is given certain parameters like the geometry and the pressure difference on both sides, you can find all of those things and you can find them essentially exactly, anything that you want to know. Because things are kind of orderly and well behaved, and we can solve them easily, either by analytical methods, which we've used a lot, or if you have something more complicated, you can solve it easily numerically. Turbulent flow, not so much. So in turbulent flow, in turbulence, the flow has mixing. So this is essentially from this component in Navier-Stokes. So the Navier-Stokes equation still is true for turbulent flow as it is for laminar flow, but essentially this fluctuation or this mixing becomes really, really, really hard to actually model. So we have mixing at varying time and length scales. So there's no really straightforward, you can't come up with exact analytical models anymore, like you have no hope, but you can't even come up with very good computational models. Even that's super, super hard because you have multiple length scales that things are happening at and a wide range of time. So if you wanted to solve, right, exactly, you basically need to solve it down to like individual atoms, and you have so many of them and they're all doing, you know, everything that you can't solve it anymore. So you have such widely varying time and length scales, your models kind of go to crap. So what we end up having to do is use, well, let me draw a picture. So if this were our pipe, kind of the defining feature of turbulence is you know, you might have the velocity is going from left to right, but you can have like swirls and eddies and vortexes and mixing and stuff happening, right, all over in your flow. And you saw that maybe a little bit, and you've seen that in a lot of different things, right? You get, if you look at the, you know, smoke rising out of a smokestack, you can see it swirls and whirls, and you get vortexes and eddies and all sorts of fun things like that. This means that we need to start using semi-empirical models. So even computation becomes pretty, really hard, to where there's a lot of art into it. You have to really try to understand the system and understand your model and how you're approaching it computationally, where there's a lot of work and art that goes into even making a computational model that can accurately handle a certain situation if there's turbulence in that flow. But there are still some things that that it kind of generally can help us think about it or describe it. So this still obeys the no slip condition. So the no slip condition still works. The velocity at the surface, at the wall, is still going to be 0. And the last thing to note, right, it's essentially arising from time-dependent fluctuations. So when we watch the right, this tank draining, we have the level in the tank dropping smoothly, but what's happening is the velocity of the stream shooting out is fluctuating a little bit. It's varying a little bit in time. So we have these time-dependent velocity fluctuations. And those are what give rise to turbulence. So if you have laminar flow, essentially those fluctuations don't really matter. Turbulent flow, those fluctuations are winning. So you have turbulent flow or turbulence occurring when any small fluctuation is not damped out by viscosity. So this is really the key insight. So turbulence, one of the things about it, right, we need to know when it's going to be happening and when it's not going to be happening. So the way that we can look at that is, right, when is viscosity going to win? And when is some small fluctuation, like, you know, thinking of the tank draining, there's the inside surface of your pipe is not perfectly smooth. It's going to have some small roughness to it. A fluid particle is flowing in that pipe. It's going to hit one of those little tiny, like microscopic bumps on your pipe surface and kind of bounce upward a little bit. Viscosity is going to dampen that out and say, okay, no, we're going this way down the pipe. But if the flow is fast enough, when that fluid hits that little tiny piece of roughness on the pipe, there's going to be like a cascade of that's going to eventually result in mixing. So you have to look at it, when is viscosity going to win and when is inertia going to win. So that's essentially what we're going to look at, is we're going to look at the balance between viscosity and inertia. And we'll do that by looking at the Reynolds number. Probably the most important number in fluid mechanics, the Reynolds number. So the Reynolds number is equal to the ratio of inertial forces divided by viscous forces. So it will essentially tell us, when does inertia win, right? So if a little fluid particle kind of bounces off in a different direction, when is that going to crash into the next one, which is going to crash into the next one, which is going to crash into the next one and cause this cascade of mixing, versus when is viscosity going to win, and that small change in velocity is going to be smoothed out so that we maintain laminar flow. So our equation for that is rho V L over mu. We're right, density time or velocity times length, that's from inertia, density and viscosity, or viscosities from obviously viscous forces. So V, just to define some variables, V equals the average length. L is the characteristic length. So it's kind of a hard thing to define. It's the length that matters for whatever system you're talking about right then. So if you're talking about a pipe, If you're talking about flow inside of a pipe, then the characteristic length is the diameter of the pipe. So how big is the pipe? That's the length that matters most, not like how long the pipe is, it's the diameter. If you're talking about flow like over a surface, like the St. Joe River, if you're talking about the river flowing over the surface, we saw a sharp transition right at a certain like length down the dam. So that's actually the characteristic length for flow over a surface, is how long have you been in contact with the surface? If you're talking about like flow over an airplane wing, it's what they call the chord length, how wide the wing is. If you're talking about flow over top of like around a ball, then it's the diameter of the ball. So this characteristic length L depends on the specific geometry. There's not really a great way to know beforehand, for this system, this is going to be the characteristic length. It's kind of, once you get practiced at it, you can look at a system and say, okay, this is the length that probably matters the most. It's not like the width, it's going to be the length that we go down it, or it's going to be the diameter of this system. But it's something you kind of have to get practiced and be able to look at and figure out. L is width for a channel. Equals what do you say? Like the length along an object for flow over the St. Joe Dam, the length like down the object. And usually, so there's a fairly sharp cutoff for a given system or given geometry. So it changes a lot depending on if you're looking at flow in a pipe versus flow in a channel versus flow down the dam on the St. Joe River. Exactly where the transition is going to happen from this nice smooth laminar flow to a kind of more turbulent mixing, more dynamic flow. Exactly where that happens, what number the Reynolds number is, varies for different systems, but there's going to be a fairly sharp transition between those two different flow regimes. So for flow, flow in a pipe, we'll end here. If the Reynolds number is above about 2300, turbulent. Just to give a little bit of an idea, so between parallel plates, Reynolds number above about 1500 is turbulent. So you can see there's not like a hard and fast rule, but for a given geometry, it's fairly, if you're below 2300, you're laminar. If you're above 2300, you're turbulent. That's a simplification. That's not exactly real life. If you're super, super careful, you can keep laminar flow far beyond 2300, right? If you do things in your experiment to make sure there are no fluctuations anywhere, and you have the smoothest possible pipes, and you have, the flow everything is kept as fluctuation free as possible, then there won't be any fluctuations to kind of start the cascade. And then you can keep it up. There have been experiments where even as high as 100,000 Reynolds number, things are still laminar. But as soon as like one little tiny fluctuation starts, right, it's like balancing golf balls on top of each other. Like you could do it, but as soon as like somebody bumps the table, then everything falls down. So the same kind of thing. Once you get above 2300, that's like, the one little tiny change is all of a sudden going to start a cascade, and then things will be turbulent. So we'll talk more about turbulent flow, how we model it, how we can think about it. Yeah, Josie? Speed? No, velocity. Velocity. Speed. Sorry. Average velocity. My mistake. Thanks for catching that, Josie. So we'll talk a lot more about the Reynolds number. We'll talk a lot more about turbulence, and we'll jump into that next time.
Yeah,